Okay, so our next talk is by Cat Joyce. It's Who Watches the Watchers in Web PKI?
Hi. Yeah, I'm Kat. It's great to be here. Today I'm mostly going to be talking to you about something called certificate transparency. So yeah, before we get on to what certificate transparency itself is, I want to sort of start off by talking a little bit about, oh wait, how do I get it to change? Hold on a second. There we go. I want to start off by talking a little bit about the problem that certificate transparency was sort of intended to help with when it was sort of dreamt up. So I want to start with an example, and this is where I have to put my hands up and say, I do work at Google. The example is a Google example. It was the only way I could get my slides approved. Please bear with it. So we're going to start off. Say you are a Gmail user and you want to log into your email. What are you going to do? You're going to go to mail.google.com, hit enter, and type in your login details, and a web page is going to appear that probably looks something a little bit like this. Now, the more observant of you will notice that up in the top left-hand corner, there's the beginning of the URL has gone green, and there's this very reassuring little padlock symbol and the word secure. And what this means is you have connected to the Google web servers securely, so everything is encrypted, and so that anyone listening in on the connection can't tell what's being said. Okay, great. So you've got this secure connection. Yay. But what happens, how do you know that it's actually Google you're talking to on the other end of this connection? How do you know it's not someone just pretending to be Google? How can you be sure that when you type in your login details, you're not actually sending them to an impersonator? Well, this is where we start talking about certificates. A certificate is a thing that a web browser sends to a web server sends to a web client to prove that they are who they say they are. And a certificate contains two things. It contains a public key, and it contains a domain name or a web address. And what a certificate means is that if you use this public key to set up a secure connection, you can be sure that you're talking to the real version of this web address. Now, for a certificate to be accepted by a browser, the certificate has to be signed by one of these trusted entities that we call certificate authorities, or CAs. So going back to our example, say you're Google and you've got this website, mail.google.com, that you want your users to be able to connect to securely. You're going to need a certificate to be able to present to your users when they try to connect. So you go along to a certificate authority and you say, hi, I'm Google. I've got this website, mail.google.com, and here's my public key. Please, can you issue a certificate to me? The certificate authority will take this information, and it'll take a look at it, and it'll run a bunch of checks to convince itself that, first of all, this is actually Google it's talking to, and that all of the information provided is both correct and truthful. And if the CA is happy with this information, it'll sign a certificate, issue the certificate, and send it back to Google for them to use. Now, this is the point in Web PKI where there's trust. We trust certificate authorities to get this right. We trust CAs not to issue certificates to the wrong people. Okay, so now, you're on your browser, you're trying to check your email. When you go to mail.google.com, Google will then respond with this certificate. It'll send through the certificate that it's had issued. And your browser will check the certificate and see that it's been signed by a trusted certificate authority, and set up a secure connection so that you can then check your email. Okay, so that's all fine. That's sort of how the system was intended to work. But then what happens if a bad guy comes along and says, goes to the certificate authority and says, hi, I'm Google. I've got this website, mail.google.com. Here's my public key. Please, can you issue a certificate for me? Like I said, we trust certificate authorities to do the right thing here. We trust CAs not to issue certificates to the wrong people. We trust CAs to be able to tell that this isn't actually Google they're speaking to and not to sign anything. But what if, for whatever reason, say maybe the CA is hacked or they make a mistake, say they issue a certificate that they shouldn't? Well then, when you go to connect to mail.google.com, the attacker could respond with their certificate instead. And your browser has no way of telling that this is a fraudulent certificate. You know, it's still signed by a trusted certificate authority. So your browser will set up a secure connection. But this time, when you send your login details, you'll actually be sending them to an attacker. Okay, so this sounds bad, right? You know, you might be saying, okay, this isn't great, but is it something that really happens? Is this really something we have to worry about? Unfortunately, it is. There are a number of examples that I could have used here. The one I've chosen is the one that was like one of the real sort of inspiring incidents that sort of set off certificate transparency. So it's one of the sort of more relevant ones to us. Back in 2011, there was a certificate authority called DigiNotar. And what happened here was they were hacked. And the attackers managed to issue a wildcard google.com certificate. So what actually happened here was DigiNotar apparently actually detected the breach when it happened, but you know, being hacked is bad for business, so they decided not to tell anyone. They thought they had contained it. And it was actually something like 3 months later that a user sort of noticed this fraudulent certificate floating around and being used and then reported it back. And then after some investigation, it turned out that the attackers had actually got hold of not just one, but something like over 500 fraudulent certificates for a number of like, you know, big name domains. And yeah, DigiNotar is no longer a CA, let's put it that way. So we've got, you know, there's clearly a problem here. The problem is this blind trust we have in CAs to just do the right thing and not misissue certificates. But what this example really shows is the problem is actually more than that. It's if a CA does misissue a certificate, we have no way of telling that that's happened without them sort of owning up and saying, look, we did this. And there's actually no guarantee that they necessarily know this has happened. So what can we do about that? Well, this is where I bring up certificate transparency. This is enter certificate transparency. What is certificate transparency? So it's an ecosystem to detect certificate misissuance. Now, I emphasize the word detect because we're not preventing certificate misissuance. It turns out that's actually a much harder problem. Within certificate transparency, there is this core concept, this idea of a certificate transparency log. And what that is a publicly auditable, append-only certificate store. So that means it's just essentially a big repository of certificates that anyone can access, anyone can add to, anyone can go and see what's in there. There are certificate transparency logs already in existence, and they can be run by anyone with the technical capacity to sort of keep them up and running. Currently, they're mostly run by large tech companies and certificate authorities, but really they could be run by anyone who has a sort of a vested interest in the security of the internet. In fact, there was actually a guy who we met up with. He was super enthusiastic about certificate transparency, and he told us, he was like, yeah, I'm running this CT log, it's called Behind the Sofa. We were like, what? And it was literally running on a box behind his sofa. So you know, anyone who wants to do it, you can run one. How reliable they are, that's a different question. So the goal with these logs is to get all of the certificates that are used on the web into certificate transparency logs, so that then, if you're a domain owner, you can monitor these logs. You know, I mentioned they're publicly auditable, so you can monitor them and keep an eye out for certificates for your domain. And if you see a certificate for your domain that either you didn't ask for or that doesn't contain your public key, you can then take the necessary steps to get it revoked. Okay, so before we had this system where you know, CAs were just blindly trusted to not to misissue certificates. Now we have a system where certificate transparency logs will publicly publish all of the certificates that certificate authorities are issuing. But what if a certificate transparency log lies about what's in it? What if a CT log says it's going to store and then publish a certificate and actually doesn't? What if a CT log does store and publish a certificate for a short amount of time, but then deletes it and stops publishing it? Haven't we just moved the trust from CAs to certificate transparency logs? No. It actually turns out we can verify that certificate transparency logs are behaving correctly. And the reason we can do that is because of the cryptographic data structure that is used by certificate transparency logs to store certificates. And that data structure is a Merkle tree. Now, the Merkle tree that you can see up on the screen is just one containing 7 certificates. So this represents a CT log containing 7 certificates, very, very small. And what a Merkle tree is, it's very simple. It's just a binary tree where the leaves are the hashes of the things that are containing it, in our case, certificates. So if you look at the slide, A is the hash of certificate 1, B is the hash of certificate 2, C is the hash of certificate 3, etc. And the intermediate nodes of the tree are the hash of the concatenation of the 2 children of that node. So again, if you look at the slide, to just like get your head around that, G is the hash of A concatenated with B. And then K is the hash of G concatenated with H. And that trickles all the way up to the top, where you get the root of the tree, or what we call the tree head. Now, upon request, certificate transparency logs are required to publish these tree heads. And those published tree heads, in conjunction with this data structure, means that we can actually prove and we can check, like cryptographically check, that certificate transparency logs are behaving. So one example that I mentioned of dodgy things that a CT log could do was, what if a CT log accepts the certificate, says, yeah, I'm going to add it, I'm going to publish it, and then actually doesn't? Well, if we take that example, okay, what if we wanted to be able to check, we've submitted certificate 3 to a certificate transparency log, and we want to be able to check that C3 has actually been included in the log. How could we do that? Well, we know C is just the hash of C3, so we can calculate C. And then if we could calculate H, and then calculate K, and then calculate the tree head, we could compare the tree head with the tree head that the log is reporting. And if they're the same, we know the log is behaving, it's incorporated our certificate into its tree. Wonderful. But in order to get H, we need D. And in order to calculate K, we need G. And in order to calculate the tree head, we need L. So in order for a CT log to prove that it has included a certificate, all it has to do is provide those 3 intermediate nodes. Now, as a CT log grows, as more certificates are added to it, this internal Merkle tree is going to grow as well. And so the tree head, the root of the tree, is going to change. The value of it is going to change. And so there's a second proof mechanism that's similar to this one, but a bit more complicated, that I'm not going to go over right now, for time, that proves that given 2 of these tree heads, it proves that they're consistent. And what I mean by consistent is that the sort of larger of the 2 tree heads was obtained only by adding certificates to the previous tree head. So I mentioned CT logs are meant to be append only. This is how you can check it, given 2 sort of tree heads with associated tree sizes. And those 2 proof techniques are actually all you need to be able to check that a certificate transparency log is behaving correctly. Does it work? Yes, it does. We have the certificate transparency ecosystem, the sort of wider ecosystem, has successfully detected a number of misbehaving certificate transparency logs using these checking mechanisms. One of the logs, what happened here was they used the same public key to run both a production and a test log. Now, in the certificate transparency world, CT logs are identified based on their public key. So by using the same key for 2 logs, any tree heads issued by either of those logs were considered to be from a single log. So what happened in this case was their production log issued a tree head, their test log issued a tree head for a different set of certificates because it contained a different set of certificates. And then when asked, the production log couldn't produce one of these consistency proofs between these 2 tree heads, and that was when we sort of started figuring out something funny was going on. In the second instance, this log was actually running on, I believe, on Amazon, the AWS S3. It was running on S3 when the outage happened towards the beginning of last year. And what happened here was, so they issued a tree head, and then S3 went down. And in the panic of, oh no, all our data, everything's down, they restored from an older backup that didn't contain all of the certificates. And then a bunch of new certificates came in and was added to this older version of the tree. And they issued another tree head. And those 2 tree heads were then inconsistent because there were some certificates missing from the second one that were in the first one. Now, in this case, actually, it was, although, okay, they messed up, the tree became inconsistent, it was really, really impressive how the log operators dealt with it. The inconsistent tree head was only actually sort of being reported for something like 2 minutes, and the log operators very, very quickly produced a very detailed post-mortem of everything that had gone wrong. And there was a lot of public discussion on sort of everything that had happened here. So it was just the way that they dealt with this sort of failure was absolutely fantastic. And one of the things with certificate transparency is that we sort of pride ourselves on being transparent. So whenever something does go wrong, all of the discussion does happen in public. And because CT is, it's still quite new, it's still quite young, we're still learning. And so every single one of these war stories, although something did go wrong, we learned something from it, and something good came from it, and we learned how not to mess up in the future. So that's pros and cons. Okay, so sorry, we have certificate transparency sounds like a great idea, right? I'm biased, but yay. But how do we actually incentivize people to use these logs when we've got them spun up? How do we incentivize people to put certificates into certificate transparency logs? Why would they want to do it other than sort of like for the good of the internet? Well, the answer to that is browsers. So as of April 30th this year, Chrome started requiring that all newly issued certificates have to be present within multiple trusted certificate transparency logs to be accepted. Safari currently requires this for a specific subset of certificates. So Safari requires this for something called extended validation certificates, or EV certificates. And EV certificates are basically the ones that make your sort of URL bar look like this. Yeah. But as of October this year, Safari will also require that all newly issued certificates be present in multiple trusted certificate transparency logs to be accepted. So, this is becoming certificate transparency has basically become part of the web PKI. And there have been a number of discussions with the other major browser vendors, about supporting certificate transparency too. So that's great. Now, I've mentioned a couple of times this. Okay, on the previous slide, we had these certificates have to be present in trusted certificate transparency logs. What do we mean by trusted? I said, oh, you don't have to trust them. So what does that mean? And what trusted really means is that certificate transparency logs are CT logs that are behaving correctly. Now, Chrome specifically has a log policy that dictates what its perception of behaving correctly is. And it includes things like conforming to the certificate transparency RFC, maintaining 99% uptime so that you can access it to actually monitor and check for domains. And there's a handful of other things in there, but one particular one is that when a certificate is submitted to a log, the log has to incorporate it into its Merkle tree within 24 hours. Now, the point of this requirement is that is to sort of minimize the amount of time that it takes, the amount of time between when a certificate is submitted to a log and when it's then publicly accessible for monitoring. But then at the same time, it's trying to balance that with operationally allowing enough time to incorporate the certificate into this Merkle tree structure. Now, moving 24 hours, quite a long time, right? Like, how long can it take to actually add a certificate to a Merkle tree? That doesn't sound that hard. But in reality, what this 24 hours is the amount of time a log operator has to recover or to handle things when something goes wrong with the log. We saw from the Amazon S3 outage war story that with certificate transparency logs, recovering from failure isn't as simple as restoring from a backup. Usually there's some sort of like manual intervention needed, and trust me, if the thing that goes wrong is at 3 a.m. on a Sunday, your log maintaining team are going to be really thankful they have 24 hours to handle it. That being said, 24 hours is not long enough for all logs. So, one log did actually manage to incorporate a certificate into its tree within 24 hours, but it was actually having problems with the external APIs. So that certificate, although it was sort of technically in the tree within 24 hours, the certificate wasn't publicly accessible until 36 hours after being submitted. So that was sort of technically counted as going against the sort of behavior of the log policy. Another log, which was actually one of our logs simply failed to incorporate certificates within 24 hours. Turns out it's not that long after all. No, what happened in this instance was a specific person who we are good friends with now from the University of Michigan came across, so they had been accumulating a large corpus of certificates themselves, and they realized a large number of them, we're talking about 6 million of them, weren't present in in any certificate transparency logs. And they thought, oh, these guys, their goal is to get all of the certificates used on the web into these logs. Let's help them out. Let's help them achieve their goal by submitting these to our logs. And they submitted all 6 million of them at once. Pretty safe to say this was the largest load test we have had to date. So what this resulted in was this huge backlog of certificates to be sequenced and then stored. And because of the level of consistency required when storing certificates in certificate transparency logs, 24 hours later, this was still chugging along. Some of the certificates hadn't been incorporated. So that was the end of that. But most logs don't have a problem with this 24-hour limit and are still very happily pottering along. Okay, the big question, does certificate transparency actually work? Well, I like to think that I wouldn't go around giving talks like this about it if we built the system and it was kind of failing at life. So yes, it does. Proof that it works. So we run a monitor for all of the certificate transparency logs that are out there for Google-owned domains. And we discovered that a specific certificate authority had issued a certificate for www.google.com that we hadn't asked for. Now, we went and spoke to this CA, and it turns out they would, one of their test engineers needed a certificate for testing, and they were like, oh, I need a domain for my certificate. What shall I use? Oh, I know, www.google.com. No, bad. Do not issue certificates for domains you don't own. Just, not okay. And so, while it was a testing certificate, so it was only actually valid for something like 2 days, so, the risk was kind of sort of much lower. They did say, they were like, oh yeah, no, it's okay. It never left our test environment. We found this in the Google certificate transparency log. We were like, yes, it did. You're wrong. Anyway, they are no longer a CA. Another example of the benefit of certificate transparency is something was in a Facebook blog post. So Facebook also run a CT monitor for Facebook-owned domains, I assume. And this wasn't a malicious thing. The benefit they got was one of their internal teams had used a CA to issue certificates that wasn't one of their accepted CA vendors. And so this CT helped them detect that and get the certificates revoked and reissued by an accepted CA. So, we got a thumbs up from them, which is always nice. The blog post if you want to know more. Okay, so before I can tell you sort of what the current state and what's sort of in the near future for CT, I need to start out by just saying how things started. Going back, in the beginning. We wanted to, we had this idea for CT, and we wanted to show that it was possible to run reliable certificate transparency logs, because we wanted to convince everyone to adopt this new idea, and so we needed to show to them that it can be done. And so the initial implementation of CT logs was designed to be extremely reliable and extremely robust to infrastructure failure. And what that resulted in was a design that essentially stored the entire Merkle tree in memory. And that was kind of fine, back when logs were maybe a couple of million certificates. But recently everyone's switching to HTTPS, which is great. And there's this sort of rising popularity of much shorter-lived certificates, which is also great. But that does mean that there are a lot more certificates out there. It's a big sort of shout out to Let's Encrypt at this point. Yeah, so the current largest certificate transparency log is now sitting at about 400 million certificates. It's not so feasible to store in memory. So what this kind of led to, when we saw this coming, it wasn't like now, what are we going to do? And so what this led to was me and a bunch of the guys that I work with have developed this thing called Trillion. And what Trillion is is it's a scalable Merkle tree implementation. And we use this scalable Merkle tree implementation to back our certificate transparency logs. Now, the difference with Trillion is that the Merkle tree contents are actually stored from a database instead of being stored from memory. Trillion is open source, so you can go and check it out if you're interested. We've tested it in a bunch of different ways, and we've seen that it can sort of take, roughly 2,000 QPS is sort of, heading up towards its top limit. So, potentially up to 2,000 certificates being submitted per second. That's quite a lot, right? We've tested it. We tested the size of it. Obviously size was an issue. 400 million certificates seemed like a lot. This has now been tested for a single log, 13 billion certificates. So, that's way in the future. Trillion is actually multi-tenanted, which means that 1 trillion instance can contain multiple Merkle trees. There are a few different benefits with that. Like the main one being, for each new log you want to spin up, you don't actually have to go through all of the setup process for that log. You can just in one trillion instance, you can just provision a new log in there, and it's much, much simpler and much faster. So there's sort of an ease thing. With the multi-tenancy, we've tested it to the point where, well, it says it on the slide, you can read it, but we've got 10 tenants, and shared between those 10 tenants, there are 42 billion entries. Also more big numbers, that's fun. One of the really key things with Trillion is it's not specific to certificates. So it's more of a general transparency concept. Like it's just the Merkle tree implementation. You can give it like blobs of whatever and it will store them. And this is kind of great because it gives you all those verifiable properties, with the 2 proofs that I mentioned, potentially for other applications. And Trillion provides both the log mode, which is used for certificate transparency, and what we call a verifiable map mode. Now, the verifiable map mode is essentially a verifiable key value store. So, and the way that is actually sort of, from a Merkle tree point of view, is this is a Merkle tree with 2 to the 256 leaves, most of which are empty, which is how it's sort of doable. And if you want to add a key value pair to the Merkle tree, you use the hash of the key to find which leaf to store it in, and then that's where you put the value. This is sort of great because then you can use these 2 proof mechanisms that Merkle trees provide again for a key value store to prove either existence or non-existence of specific values, which is quite fun and has a use that I'm going to mention in a minute. Okay, so Trillion, I mentioned it's not just for certificates. It can be used sort of for wider things as well. It is used for certificates. That's one thing. We're using it to back CT logs. A number of I think a couple of CAs are also using it to back their CT logs, which is great. It's being used at the moment for something called key transparency. Key transparency actually uses both modes. It uses the log mode and the map mode. And the idea with key transparency is to target secure end-to-end messaging. So that's fun. It's also being used by DeepMind, who are using it DeepMind's doing a lot of work at the moment with health data, with NHS health data. You may have read about it in the news. And obviously health data is very sensitive, and people accessing health data when they shouldn't be is bad. So DeepMind are going to be using Trillion to keep a sort of verifiable log of all the data accesses that they have. So then if someone does access the data in a way that they shouldn't, at least they'll know because they can't go back and tamper with the access log. And then there have been a number of other sort of ideas for what to do with Trillion that have been floated. So there have been some chat about binary transparency. There have been discussions about firmware transparency. There was some discussion in sort of the early days of Trillion with the UK government about using it to help prove the integrity of a bunch of the registers that they maintain. So things like the Register of Countries, like Register of Land that the Land Registry keeps. There's also apparently a register of all the cows in the UK, which was news to me. This actually made me laugh a little bit because I believe like a few years ago, someone was telling me about the old school, like tech interview questions that were really abstract. Like, oh yeah, if you had to calculate how many cows there were in the UK, how would you do it? There's a register. That's how I would do it. Yeah, and so, if any of you guys have any more sort of ideas for uses of Trillion or anything like that, come and chat to us. Like, I'm here, a bunch of the guys from the team I'm on are here. We would love to talk to you about your ideas. That'd be great. And that's it.
Thanks very much. We've got time for really brief questions, I think. We've got one in the middle. He was first, I think.
Hello. That was a fantastic talk. I was just wondering, so when you've got billions of things in a tree, and I want to calculate whether the tree head is actually accurate, how fast is that? Because you were talking about sort of 6 million going in was quite slow to calculate. If I want to prove that the CT is accurate, is that something I can do, or?
So what do you mean? Do you mean like check that the whole tree is consistent?
I guess so, yeah. If I've downloaded a certificate transparency log from Semantic or whoever, how hard is it for me to prove that it is?
Build it all the way.
Yeah.
So hardish. So basically, currently in certificate transparency, there are a number of like monitors that are doing exactly what you're saying, like downloading the whole tree and building it up, to calculating every single in-between hash to check that that final hash like meets the one that the log's reporting. And those monitors are very good at. If it doesn't, they will get in touch with well, it's all on public mailing lists. They'll say, look, it's not. In terms of like it depends what you want to do. It depends what your use case is. For sort of like site owners, they maybe don't care as much about that. They're just like, other people can be checking the integrity of it. If Chrome trusts it, then kind of thing. But in terms of the two proofs that I showed, so if say you're a CA and you submit a certificate to it, and then you want to check that that certificate has definitely been included, the number of nodes you need is log n because it's a tree. So that's much quicker, that's super quick. Verifying the whole tree can take a bit more time, but actually the sort of challenge there is downloading the whole tree. So there's sort of different things.
Okay, this chap, and then I think other questions will have to be offline, I'm afraid.
Yeah, come and find us after. Happy to talk.
Yeah, so I was just wondering, you said the tree is currently at 400 million certificates. How big is that in terms of like gigabytes?
I don't know. Do you guys know how big that is in terms of gigabytes? I'm getting it from my boss, so we don't know. No? We haven't looked. I can look. We can look and we can tell you if you want. Yeah.
Okay, thanks very much. Let's show our appreciation.